Okay, this is problem 8.6. So this is a centroid problem, a little different than the ones we've already looked at. This is dealing with a manufactured shape. So we have a manufactured shape here. Now we have a normal rectangle up here. This is a rectangle. It's a plate. It's 12 inches by 1 inch here. This is what's called a W, 10 by 45. So we're going to go back and look at the Appendix A to get that information. The good news is most of this is here. So what we'll need from this is this dimension here along the flange. We need the distance from flange to flange, which is this distance here, and we'll need the area. And we also know in this problem that we're going to be using this as our origin. So this is going to be our X direction, and this will be our Y direction. So let's take a look at Appendix A, and we're looking for this W 10 by 45. So we go to Appendix A. This is Appendix A. Notice in the shape list, there's your W's. W shapes are I-beams. What we have is a 10 by 45. So the 10 by 45 is down here. The 10 basically is referencing the depth, although that's in general, so that's not exact. And the 45 is the weight of this thing per foot of distance. So notice in here, we have several things that we'd be looking for. First off, highlight this. We have this guy right here. There's my W by 45. Area 13.3. The depth, and notice up here in this chart, it's really critical. We have this depth indication. From the top to the bottom of that flange is 10.1. Also notice there's another one over here. You're always going to use the one that's the more exact. This is for steel detailing, so we want to make sure that we use the exact one. So then we also need to know what this BF distance. BF is what you call your flange width. So we're looking at the flange width, and that's this guy here. So BF turns out to be 8.2. And that'll be all the information we'll read right now. So we're going to copy this back over on our diagram. So we determined this to be 8.02. The depth was 10.1 inches, and these are all in inches. And we have an area that was given as 13.3. So what we're going to also know is recognize, and let's go back onto this real quick. It doesn't give us any moment of inertia, or doesn't give us any X bar or Y bar information for your axes, because what this is indicating to you is that the X is exactly in the middle. In other words, it's half of D, and that YY axis is exactly half of this flange. So it's going to be half of B for the X bar distance, and it'll be half of D for the Y bar distance. Now we're going to see when we get into channels that'll change a little bit, and some of the other types of shapes, but for the I-beams will work it that way. So we'll go back here. So we're going to set up our chart. So we're going to have shape. We're going to have area of that shape, the X distance, the AX value, the Y distance, and then the AY. So let's go ahead, we'll indicate this as, this will be our shape 1, and this will be our shape 2. So shape 1, we said from the chart, is 13.3 square inches. So X is the distance over to the YY axis, and so because of this type of thing, the symmetry of this shape, it's going to be half of that. So that gives us 4.01. Multiplying the area times the X, we get 53.33. And these will round out further or go out further. A lot of times I'll take them out 3 and round things in at the back at the end. Okay, so the y distance is half of the distance this way, half of the depth, in other words. So from the chart, it was 10.1. So that'll make this 5.05. And then we're going to multiply the area times that, and that gets us 67.165. So now we're going to look at shape 2. Shape 2 is just a shape 2 that you would use using the table in the book 6.1. So basically, we just have an area of 12 times 1 for that plate. So that is going to be 12 square inches. The x distance, because this is symmetrically put on this thing, the midpoint of that will coincide with the midpoint of the I-beam. So we're going to have the same point, or the same distance over will be at 4.01. If this thing was kicked one way or the other, that would be different. You'd have a different x value. But in this case, we've got symmetry again going on. So 12 times that gives us 48.12. And then the y value, so the y is going to be the total distance from the origin. So we're going to go 10.1 up plus the distance to the centroid of that plate. So that's half of 1, so that's a half. So we're going to take 10.1 plus a half, which is going to give us 10.6. We're going to multiply that times our area, and that gets us 127.20. Okay, so we have everything we need, so we can now do our sums. So we'll sum the area, 25.30, sum the AXs, 10.453. We're going to sum the AYs, 194.365. So our x bar distance is the sum of the AXs divided by the sum of the area. And this turns out to be 4.01. And then the y bar distance, 194.365 divided by the sum of the areas. And that gives me 7.68. So let's think about this, and it should make sense. Let me do a little erasing here. I'm going to erase some things so we can see. What we got going on is the fact that this is exactly midway here. So it should make sense. Notice these are all the same. So it's symmetric. If we go in there and we drew that location, what you got going on is your centroidal y-axis is something like this. So this would be our x bar distance, like that. So that's my x bar value. And that's symmetric. And if we look at the y, think about this. Half of this is the 505, and because you got this plate up here, it's shifting that location of where that the centroidal axis is. So that would put this guy coming up like here to here from the origin. So it's pushed it up, and that should also start to make sense to you with the way the centroids are working. So what we have here then is this is my y bar distance, and my centroid is somewhere about right there.